Hello viewers, welcome to our online lecture. Today we will be doing the important topic in organic chemistry. I, Dr. Archana Chaube, Faculty of Science from the Bhopal School of Social Sciences. Our topic for today is aromatic nucleophilic substitution reaction. In the last lecture we discussed the various types of organic reactions, among which we dealt in detail the type of substitution reaction. We have seen that substitution reaction can be categorized into various forms depending on the steps which are involved in it, or the number of species or the reacting species which affect it. So, we know that substitution reaction is broadly can be categorized as electrophilic and nucleophilic substitution reaction. Today we are dealing with nucleophilic substitution reaction in aromatic compounds. So, let us begin. The topic that we will be covering today are aromatic nucleophilic substitution reactions, the reason behind these reactions, the specific two examples, that is SNAR mechanism and benzene mechanism. Now, as we know that under normal condition, aromatic compounds or the aryl halides, they do not undergo nucleophilic substitution reaction, because we know that nucleophiles are which species? Nucleophiles are species which are nucleus loving, that means they are itself negatively charged species, and the aromatic ring has dense negative charges. So, it is not a regular type of reaction that can occur very easily without certain specific conditions. If we talk about the reasons why the aryl halides do not undergo nucleophilic substitution reaction, here are a few of them. The carbon halogen bond that we see in aryl halides, it is sp2 hybridized, and whereas when we compare it with alkyl halides, there the carbon halogen bond it is associated with sp3 hybridization. So, as we have studied about hybridization, we know that in sp2 hybridization and sp3 hybridization, the character or the percentage of contribution of s and p orbitals is different. The more the s orbital comes in contribution, the bond length becomes shorter. So, that is the case in case of aryl halides. We see that due to sp2 hybridization, the bond length becomes 170 ppm, whereas in case of alkyl halides, it is 177 ppm. So, as the bond length is longer, the dissociation becomes easier. So, that is why this is one of the main important reasons why it is expected that the aryl halides will do not undergo substitution reaction very easily. The second reason behind this is that we know that the halogen atoms comes under the category of such species which have electrons on them. The lone pairs are available. So, the lone pair which is present on the halogen, it comes in conjugation, it participates in conjugation with the pi electrons of the aromatic ring, and due to this particular phenomena, the carbon halogen bond in case of aryl halides, it starts showing a double bond character, and we also know that the bond length of the shortening of the bond length in case of aryl halides is due to the presence of this double bond character, because the single bond is normally longer in comparison to the double bond. So, here we have seen why a aryl halide should not show nucleophilic substitution reaction, but since we are showing that it is one of the important category. So, let us see how this reaction becomes successful in case of aryl halides. Aryl halides undergo aromatic substitution reaction which is termed as SNAR. This is the short form that we use for aromatic nucleophilic substitution reaction. So, in case when the aromatic ring has, like if I draw a benzene ring over here, and this benzene ring, if it has a nitro group attached to it or any such electron withdrawing group, the electron withdrawing character of this group, it will facilitate a condition in which there will be the density of electron will decrease at particular position, that is the ortho and para position within the ring, and thus facilitating the nucleophilic substitution reaction. So, therefore, we say that in aromatic ring the nucleophilic substitution reaction can only occur when presence of strong electron withdrawing groups are there, and these groups, their position is also specific, that they should be present always at the ortho and the para position, because we know that the directive influence of the group directly affects the ortho and the para position and indirectly affects the meta position. So, let us begin with the example of conversion of para-chloronitrobenzene into para-nitrophenol. When the para-chloronitrobenzene undergoes substitution reaction, substitution of chloride with the hydroxyl radical occurs, and as we have seen that an electron withdrawing group, the nitro group is present over here. Because of this group only, the substitution of OH minus, which is a strong nucleophile, it will go and substitute it is a nucleophile, and it is going to substitute the another strong nucleophile, which is the chloride ion. So, OH being stronger than chloride, it goes and substitutes, but this substitution is only facilitated because of the presence of the nitro group, and that too we have discussed at the ortho and the para position. If we see the mechanism of the reaction, it is very clearly seen over here that the first step, which is the rate determining step, is the attack of the nucleophile. Our hydroxyl group of the nucleophile goes and attacks at the point of lesser electron density, and how this electron density gets reduced, it is seen over here in these resonating structures, where the nitro group tries to attract the pair of electron towards itself, and the electron, these direction of the arrows, they are representing the movement of electrons away from chloride. We can see the arrows are moving away from chloride towards the nitro group. So, in all these three resonating structures, we can see that electron density is increased at the other positions of ortho and para, and the hydroxyl group, obviously in comparison to this, the position where the hydroxyl group is attacking becomes more positive. So, therefore, the nucleophile comes and attacks at this place where it is finding lesser electron density. So, actually the electrons are indirectly being decreased at this position because of the directive group effect of the nitro group. So, we can summarize that the resonating structure that is being created because of the resonance of these pi electron is denoted by this structure as A. Now, since we know that the attack of nucleophile is this step is a slow and the rate determining step, therefore, this is one of the major step. After this comes the fast step, that is the removal of the chloride ion, which results in formation of para-nitrophenol. There is another important example of aromatic substitution reaction, which is the formation of benzene as an intermediate. Now, what is benzene? Let us look. Now, as discussed before, nucleophilic aromatic substitution reactions are when they take place, like in case of chlorobenzene, in presence of a strong base. When this reaction occurs, the resulting product is the substitution by an NH2 group. But when this substitution occurs, normally it is being assumed that there has to be an addition elimination mechanism. But here actually instead of addition elimination, the product the triple bond is being formed and it results in formation of benzene. The structure that we see over here is a benzene. What is benzene? The normal benzene ring with one of the position of carbon having a triple bond. So, because of the presence of this triple bond in benzene, it is a very strained molecule, it is not a very stable molecule. Therefore, this is not the final product of the reaction, it does not stay in this place, instead it is being very easily attacked by any of the nucleophiles which are in search of the centers where there is where they can go and attack. So, here is the mechanism, and when we discuss this mechanism of attack of the nucleophile on the benzene, we can see that there are probabilities of two types of products that can be formed, which are the para and the meta. Both type of products can be formed. So, how do we decide which product is the major and the minor? But actually the mechanism, when it is being studied, it is found that both the products occur in 50-50 ratio. That means the probability of the para and meta product to be formed is equal. So, why this is so? Let us see the mechanism over here. This mechanism is showing the pathway of formation of the substituted product on benzene. Here is our benzene molecule and it has the point of which I am representing as 1 and 2 is the place between this is the presence of the triple bond. So, because of this triple bond, the carbon is having a short of electron over here and the NH2 group will come and attack at one of the position either at first carbon and automatically hydrogen get attached at the second carbon because both the positions are equivalent. So, the attacking group can first come and attack either at first position and the hydrogen attaches to the second position resulting in formation of this A product, or vice versa, that the entering species can go and nucleophile can go and attack at the second carbon and hydrogen gets attached to the first carbon resulting in the formation of the product B. So, this is the mechanism that we can see that how in first state when the ammonia molecule goes and binds over here at carbon number 1, the nitrogen, because it has the ability to form only 3 bonds, but it is forming that 4th bond due to which a positive charge develops on which, and immediately it results in the release of a proton from here, and this proton will go and bind at the sp2 hybridized orbital of benzene resulting in formation of the product A. Similarly, if we go the other way around, the mechanism remains the same. It is just the attack of the ammonia molecule instead of the first carbon position, it goes and attacks to the neighboring carbon resulting in formation of the second molecule. So, the probability, since both are equivalent, so the probability of forming of the two products, that is the meta and the para products, becomes equal. So, today in this lecture we have discussed the substitution reaction in aromatic compounds, the nucleophilic substitution reaction, and we have taken two products, formation of para-nitrophenol from para-nitrochlorobenzene and the mechanism of benzene formation. I hope you have understood the topic. In the next lecture, we will continue with some other important reaction mechanisms. Thank you.